In this video, we are going to learn to see things. Okay, not just things, but seeing structure. You've seen and heard these words many times, but let's try to summarize and explain what we mean by structure and how to see it. Alright, so structure is a pretty vague and confusing general term here, and it may have many different meanings. So in this specific context, we are going to talk about several formulas or several rules that we've learned, in particular when we factor, and they're structured in a certain way that recognizing this pattern will help your life, will make your life easier. We are going to talk about couple factoring methods today. In particular, you learned greatest common factor technique, right? So the idea of this is, if you have a common factor, factor means multiplying, in two or more terms, let's say a times b plus a times c, maybe also a times d, then we can factor it out. So the idea behind greatest common factor is basically the distributive law, just going backwards. Instead of distribution, we are undistributing. Another formula that we learn is the difference of two squares, which technically is squaring of a minus squaring of b results in a minus b times a plus b. There are a couple more we are going to talk about, but let's talk about these two first, just to understand what we mean by using structure. So for example, you have a problem like this. 3x minus 5 times 6x minus 9 plus 3x minus 5 times 7x plus 3. One way to work with this problem would be to multiply it all out. Multiply all of this, combine like terms, and then hopefully there will be some common factors. Again, the goal is to factor. But if you look carefully and notice, the key word is seeing. So let's look. What do you see? You see that these guys are exactly the same. So this is your common factor. Let's look at this. If you call this A, it's the same thing. Now, this is something else. So let's call it B. And let's call this C because it's different. So this is our structure, the same as we had here. We have a common factor which we can pull out, A times B plus C. So we are using this structure to work with our original problem. So 3x minus 5 is your A. It's like one common thing we can pull out from both terms. I prefer to write brackets here because this is parenthesis, this is parenthesis, this is your B and C that you're going to combine. So it's 6 minus 9, you can keep it in parentheses, plus 7x plus 3. You can keep it in parentheses. It doesn't really matter now, but in the next example, I'm going to give you a minus here, and then this parenthesis will really matter. So once you notice that 3x minus 5 is a common factor, you pulled it out, left over 6x minus 9, 7x plus 3. This is your B and C that you combined. Now you can just finish simplifying. In brackets, you have 6x plus 7x, 13x, minus 9 plus 3 minus 6, and you're done. Let's look at the problem, which is a little harder. Again, let's see first. Let's look. You see that these two guys are the same. Ooh, they're not in the same place. Does it matter? Not really, because of the commutative property, these two can be easily switched around, so it really doesn't matter. We can still factor out our common factor, 2x squared minus 5. Let's do that. 2x squared minus 5, common factor, goes out. I put brackets. And because I need to combine these two pairs of parentheses, I keep parentheses, especially because of this minus. I really need to be careful about this. So 7x minus 3 is the first leftover, minus the second is 5x minus 4. Now you can see why these brackets and parentheses are important, because as I'm going to combine them, I will need to change the signs because I'm subtracting the second binomial, 5x minus 4. I need to write 7x, never mind, 7x minus 5x, 2x, and then minus 3 plus 4, so that will be plus 1, and that's my answer. If I did not take care of my brackets and parentheses, what happens often, people do this, 7x minus 3 minus, and then I just keep copying, 5x minus 4. This is wrong, because I'm going to subtract this entire thing. So I am subtracting minus 4, and it will change sign. Let's look at a different example. If you need to simplify this expression, first thing that comes to your mind probably is to square the first one, square the second one, combine like terms, and then hope for the best. It's a lot of work. So let's look very carefully. Hint, look for structure. Try to recognize something. Do you see this squared and this square? So the structure we deal here with is square of one guy minus square of the second guy. So what we can do, we can factor it as a difference of two squares, a minus b times a plus b. A and b are my binomials. It really doesn't matter what it is. Whatever is squared minus something else squared, it's a structure. Whatever is inside of this square and inside of this triangle, it will always be the same case. This and this, and this and that. That's what we mean by structure. So imagine now this binomial inside of this square, this binomial inside of this triangle. So what we need to do is, we are breaking this now into a product of two binomials. I'm using brackets. You already know why, because something else will be happening inside of these brackets. So this is my first bracket, this is my second bracket. Actually, I'm going to switch them around. I want to start with the sum. It really doesn't matter. So my sum will be first, my difference will be second. First, I'm going to add my two guys. It's square of 5x plus 2 and 3x minus 1. So my first binomial is the sum of these guys, and then it will be the difference of the same two guys. And you already know why I want to be careful with parentheses, because whenever we have subtraction, we have to be really careful. So now we need to simplify within each bracket. 5x plus 3x, 8x plus 2 minus 1. Plus 1. No problem here. Now I can write parentheses instead of brackets. It doesn't matter. In the second case, I have to be careful again because of this subtraction. I will need to change my signs. So it's 5x actually minus 3x, which is 2x, and then plus 2 minus negative 1. So it's 2 plus 1. So it's plus 3. This is it. We factor it. Much easier than go back and imagine if you square this, then you have to subtract anyway. And there are many mistakes possible on the way. There can be many variations of this which we are not going to consider here, but in fact you can square whatever minus square of whatever, and whatever happens here, you would have the first guy, let's call it A, second guy, let's call it B. So we are going to have A plus B, the first thing plus the second thing, times the first thing minus the second thing. That's what we mean by structure. And in this case, we looked at the structure of difference of two squares. Let's consider a couple more cases and some different structures. So let's look at this problem. That looks kind of messy, but if you look carefully, and again, seeing is the key, right? If you look carefully, you recognize that this and this is the same thing. You cannot really factor it out from the whole expression because this term doesn't have it. So greatest common factor idea will not help. But let's keep looking at the structure. We see that this is the square of something, and this is the square of something. So what should come to your mind is the idea, maybe it is a perfect square trinomial. Let's see. So this is clearly a square of 2x plus 3. This is the square of 5x. Now, if you're lucky, then this will be a double product. Let's see. If you multiply 5x by 2x plus 3 and double, that's exactly what we are getting here. Now, because this is a minus, we must have a minus between these guys, and what we have is the perfect square trinomial, where the first guy is 2x plus 3, and the second is 5x. And we can simplify it now. 2x minus 5x minus 3x plus 3 squared. We can leave it like this, but actually, I don't like to start with a minus. I'm a positive person, as you know. So the thing is, minus 3x plus 3 is opposite to the expression 3x minus 3. And in this case, it really doesn't matter because we are going to square it. I don't want to confuse you here, but the idea is, if I write 5 squared, it's exactly the same as minus 5 squared. Both of them are 25. So I just want to rewrite it nicer. But that's not the point here. Let's look at one more example. This is a pretty complex expression. It's a fourth degree. Oh, by the way, try to do it. I think you've seen something like this. Pause, try to do it, and then get back to me. Okay, hopefully you did it. So now let's look at it together. That is definitely not a perfect square because 8 is not a square. But a structure of this still kind of reminds us quadratic trinomial. It's not really quadratic, but in some sense it is. There's no x, but there is x squared here. And this x to the fourth can be seen as x squared squared. So if you look at this like this, it is quadratic with respect to x squared. So if instead of x squared there was just an x, I don't want to write an x. And some people suggest using substitution. You can do that, but let's just try to imagine there is something here. It doesn't matter what it is. X squared, b, really doesn't matter. We're talking about structure here. So the structure here is of a trinomial, quadratic trinomial. Square of something minus 6 something plus 8. How would you factor it? Easy, using general trinomial idea. It would be, to get this squared, we need to have the same thing in both parentheses. To get an 8, we would need, not that many options. 4 and 2 probably. And from 4 and 2, we can easily make a 6. Minus 4 something, minus 2 something. That's perfect. So we can actually skip this part. We can go straight to this reasoning after we understand the idea. Okay, so it's a square of x squared. The only way to get it if you break it into x squared. Same reasoning as we did for basic trinomial. To get an 8, we need 2 and 4. And then if you put both minuses, it will be minus 2x squared minus 4x squared, which will actually give us minus 6x squared. And you can check it, that's exactly right. So again, we use structure of a general quadratic trinomial. Before that, we looked at the structure of the perfect square. In the previous two examples, we also look at the structure of greatest common factor and difference of two squares. And that's about it for now. You may see some more structures later on. That's it.